Let's talk a little bit today about filters. This is just a review. If you've reviewed the PowerPoints, you may have most of this information, but we thought this might be helpful for some of you who are still struggling a little bit with some of these concepts. So the first thing we want to spend a little time talking about is the source filter theory. This is a display of the graphs that go along with the source filter theory. The first graph down here at the bottom represents the vocal fold vibration. This is the source spectrum. It's a power spectrum, just like you've already seen. Includes the fundamental frequency and numerous harmonics, and you'll see here the vocal folds are drawn to represent that. Here is the filter function. This is showing what the vocal tract is doing, filtering that vocal fold vibration and making it into something else. So it's represented here in blue. This then is the output function. You can sort of see those two graphs have been combined. This is what comes out of the mouth. You'll see these graphs multiple more times in the next couple of weeks as we continue to talk about voice and speech function, but we wanted to introduce those to you now. So the whole purpose of this concept of filters is to apply it to the vocal tract and how we produce speech. In this theory, the vibration, like I said, of the vocal folds is the source of the sound, and the vocal tract acts as a filter. And it modifies that sound by amplifying some frequencies and attenuating others. So think back to the properties of sound. Any sound is a combination of its frequency, or what we perceive as pitch, and its intensity or amplitude, which is what we perceive as loudness. So really simple sounds like pure tones have just one frequency and one amplitude. And remember, the frequency relates to how fast the molecules of air are vibrating, while amplitude is how far they're moving during that vibration cycle. So again, pure tones, one frequency, one amplitude. In complex sounds, which is all of speech and most other sounds too, there are multiple frequencies with varying amplitudes which are combined. So for example, when we say the vowel oo, we have a fundamental frequency and numerous harmonics that leave the vocal folds, but they really sound just like a buzz at that level. So just having that information about the fundamental frequency would not produce a vowel that we would recognize. So, for example, an oo and an e would sound exactly the same, but that's where the filtering capabilities of the vocal tract come in to help us to create those two different sounds. It's going to modify that buzzing from the level of the vocal folds. So before we move on to talking about filters, I just wanted to refresh your memory. Recall that there are two ways that we can alter the source of a sound. We'll actually talk about a third a little later on in clinical applications, but for now we've talked about two. Frequency. We can change the frequency at which the vocal folds vibrate, and we do that by increasing or decreasing tension. So within one person, they really only have the opportunity to change the tension by contracting the cricothyroid muscle or the thyroarytenoid muscle. The other thing we can change is the amplitude of vibration. There are multiple ways to do this, but the most efficient way to do that is by altering the amount of airflow from the lungs. So if you increase your breath support, you can get louder. This is going to alter the sound slightly, but if we still didn't have the vocal tract attached, it would still sound like a duck call or some buzzing without much refinement, and certainly not speech that we're used to hearing. So let's move on then to the filters, because we're really interested then in what we're doing with the vocal tract. So what is a filter? I put a picture of a coffee filter up here to help you remember to think about the fact that filters are things that we use every day. They're things that filter your coffee, things like the oil filter in your car. They all work to allow something to pass and stop other things from going through. So a filter for sound is exactly the same. Since we just said the two main components of sound are frequency and amplitude, we want to filter based on frequency. That's the one that we can really have the most effect on. So therefore, most filters in nature are going to amplify some frequencies and attenuate others. Okay, so these are natural filters. They're going to be the bandpass type. We can also create artificial filters if we want to, using computer programs, and that's where we can really use things like high pass and low pass filters to try to filter out certain parts of the sound. But really we're working with frequency when we're talking about filters, and changing or allowing certain frequencies through. It's also going to affect the amplitude, but that's just in the attenuation and amplification piece. We're not actually choosing amplitudes with which to filter the sound. So, how do we filter the sound? Sound is filtered by reducing the amplitude or intensity to a point where we can no longer perceive it. So there are two main factors that relate to this. First, sound can be absorbed by surfaces that are relatively soft. We've talked about this a couple of times. When we're talking about the vocal tract, we're talking about soft tissues. We've talked about soft surfaces within the classroom that absorb sound. But second, sounds can sort of be canceled out as waves pass each other. So if we have an incident wave and a reflected wave passing each other, if we have an area of completely destructive interference, they could theoretically cancel each other completely out. So in an acoustic resonator, any container filled with a particular medium that's going to vibrate in response to a sound, that's possible to do, create different types of constructive and destructive interference. So think about the bottles we used in class. When you blow across the top, you're introducing the applied sound. And those sounds had multiple frequencies associated with them because they were aperiodic sounds. Then, based on the characteristics of the tube or whatever bottle that you had, the bottle amplified certain frequencies, which we hear very clearly, and attenuated the others. So even though that they were there initially, we don't perceive them anymore. And they may still be there, but they're just so small in comparison to the amplified frequencies that we don't hear them. So your initial applied sound had all those frequencies, and then the filter got rid of the ones that were outside of the passband for that particular bottle shape. So most natural filters will be of this bandpass type, which means that they amplify sounds somewhere in between two cutoff points and attenuate sounds outside those cutoff points. The point in the center, we've talked about this a little bit, called the center frequency, natural frequency, resonant frequency, is the point where the characteristics of the bottle and the medium combined to promote the most vibration. In our bottle experiment, we learned that a longer tube is associated with a lower frequency, while a shorter tube produces a higher frequency. This means that the passband for the longer tube is allowing for a range of lower frequencies to be amplified, while the shorter tube allows a range of higher frequencies to be amplified. So if we looked at that graph, the peak would just be at different points along the x-axis. The tube is tuned then based on the properties of acoustic impedance, which we had another video posted about. In general, the characteristics of the medium and the tube will determine whether many frequencies are amplified or just a few. So when we're talking about tuning of a filter, it's either going to be broadly tuned or narrowly tuned. The more uniform the tube, the more narrowly tuned the filter will be. This means that only a few frequencies will be allowed through, and most frequencies will be dampened so we can't perceive them. A tube with more bends or changes in size will result in a broadly tuned filter, so many frequencies will be allowed through and fewer will be dampened. So that relates mostly to the vocal tract, which has lots of bends in it. So why do we filter sound? There are many reasons why you may want to do that. It could be to achieve some effect in a musical performance. It could be to create an environment that allows us to appreciate music or promote sleep. Think about a nice quiet room versus a noisy one and what that room looks like in terms of carpet and wall covering and things like that. But for our purposes, what we really care about is the filtering of the sound from the vocal fold vibration is what allows us to speak all the different sounds we use to communicate. Vowels in particular are created solely by amplifying particular frequencies and dampening others. So each vowel has a distinct pattern that we not only learn to produce but also learn to perceive. We're going to talk about that in just a minute. Before we get to that, I just want to mention about quarter wave resonators. We looked at this idea, but we didn't talk about it in depth. So tubes that are open at one end and closed at the other, just like the vocal tract, behave as what we call quarter wave resonators. So that is to say, only wavelengths that are either a quarter, 3/4, 5/4, 7/4, any multiple of a quarter wavelength result in an antinode at the open end so we can hear the sound. So if you look at these up here, here's the antinode, here's the node, and this is a point of no sound at the node, point of maximum sound at the antinode. So remember our discussion of standing waves in class. When we introduce multiple waves into a tube, we get a standing wave. I'm going to show you a quick video clip to look at that. You'll note here there are multiple modes of vibration. So here we just have one antinode Here we have 2 antinodes, and you'll note that here, here, and here are all nodes, places where the slinky is not moving. Okay, here we have 3 antinodes and points of nodes in between. So if this point were to reach the end of a tube, we would have no sound. Here's another example of the next mode of vibration. Okay, so as I said, we really need to make sure when we're talking about the vocal tract that nodes don't fall at the opening of the tube or we won't get any sound. So back to our quarter wave resonator here, this comes into play when we start talking about formants. So what are formants? Formants are characteristic resonances of the vocal tract. So what does that mean? It means that the vocal tract acts like several bandpass filters put together. It creates several different areas where certain frequencies are amplified and the rest are attenuated. So think back to that image that we saw here. Here's one bandpass filter, here's a second one, and here's a third one. Okay, so it's behaving as if we have multiple bandpass filters in that system. So in general, calculating formants is based on the length of the vocal tract, and we're going to practice this in class. The simple formula that we use for the bottle activity can be used to determine the formants for a particular individual based on his or her vocal tract length. So if we use an estimated 17 centimeters for an adult male and plug that into that formula that we used of the frequency equals the speed of sound divided by 4 times the length, we get a first formant frequency of 500 hertz. Then the second formant is 3 times that value, or 1500 hertz, while the third formant is 5 times that value, or 2500 hertz. So those are values for a neutrally positioned vocal tract, or a schwa vowel, the sound. And now remember that 3 times and 5 times come in from the quarter wave resonator idea we just discussed to make sure that we have that antinode leaving the oral cavity. So how do we change formants? Before we get to that, let's look at a picture of that schwa vowel. You can see here the formants are falling at 500, 1500, and 2500 hertz. Okay, so how do we change formants? The way that we do that is to alter the shape or the length of the vocal tract. And we can change the values of the formants from those resting values at the schwa to some different values. There are some specific rules that govern how the formants shift based on movements mostly of the tongue, but of other structures as well. The first formant is inversely related to the height of the tongue. So when we elevate the tongue, we're basically increasing the volume of the pharynx, and this is going to make the first formant lower. So that's what that inverse related means. Height of the tongue goes up, first formant goes down. The second formant is directly related to tongue advancement. So as we move the bulk of the tongue forward, the oral cavity is getting smaller, and this raises the second formant. The third formant is going to be related to the position of the tongue tip, and we're really only going to talk about that related to a couple of sounds, so we'll get to that more when we get to perception. So here are a summary of those resonance rules, and the one that I haven't mentioned yet, but we talked about in class, the lip rounding rule. So if you extend the vocal tract, make it longer, it's going to move all those formants lower. You could try it by comparing a 17 centimeter vocal tract to an 18 centimeter vocal tract. You would see that all the formants were a little bit lower. The last thing I wanted to point out is the vowel quadrilateral. We'll post this so that you can see in a bigger way, but all the vowels are represented here, and we can superimpose that on the vocal tract, thinking about the first formant and the second formant, and you'll see that every single vowel has a different formant pattern, especially with F1 and F2, the first formant and the second formant, that distinguishes that vowel from any other vowel. That's the really important thing with formants that we really care about as we're working as speech-language pathologists and audiologists.